So that's why we have to have it inside the if statement. And then after that we basically print the system name. So let me just write here print f, and then we write here system name, and then we put here %s for string, and then we go to the next line, then we put a comma, and then we're gonna write here buff dot sysname, okay, which is essentially the system name. Okay, so now let me just basically copy paste it, and I paste it here. And now the second thing is the node name. Okay, and I'm gonna write here node name. Everything remains the same except here. I'm gonna write here, let me just remove this 0 from here, and from here I'm gonna write here node name. Okay, and then after that I would write here the third thing is release. So let me just paste it right here instead of typing all that. So I would paste it, and I would write here dot release, and I would write here release as well. Okay, and then I basically come out of here, and then I print here the fourth thing, which is the version. So I would write here version, and then I write here version as well. Okay, and then I come out of here, and I paste it here as well. And then the last thing that I'm interested in is the name of the machine, so I write here machine as well. So yeah, that's pretty much it. That's it. So these are the names. This is the system information that we are going to be displayed with. Okay, so we just save it, and we come here in our terminal, we clear it, and we write here GCC, then we write here our C program, and then we write here -o, and then we write here tst, which is going to be a binary file, and then we run our binary file, we hit enter, and you can see that we have the information about our system. So the system name is Linux, node name is Linuxint. Node name means our username, or the user that is currently signed in, so that is Linuxint. Then we have the release, which is 5.0.0-21-generic, and the version is 22 Ubuntu SMP, and then it was last updated on July 2 on 1:27 p.m. And then we have the machine, which is x86_64. Okay, so that's how you get the system information, and previously I have shown you that how you get the process information. Okay, so the next topic is related to file systems. All right, so the idea is that devices are represented by entries in the /dev directory. Okay, so let me type here /dev directory. Each device has a corresponding device driver which implements a standard set of operations, including those corresponding to the open function, read function, write function, and the close function that we have discussed in this file IO topic. Okay, so a device may be real, meaning that there is corresponding hardware device or virtual device driver that implements an API that is same as real device. So API stands for Application Programming Interface. A hard disk is divided into one or more partitions, each of which may contain a file system. Okay, so a file system is an organized collection of regular files and directories, and Linux implements a wide variety of file systems, including the traditional ext2 file system. The ext2 file system is conceptually similar to early Unix file systems, consisting of a boot block, a super block, an inode table, and a data area containing file data blocks. Okay, so each file has an entry in the file system's inode table. This entry contains various information about the file, including its type, size, link account, ownership, permissions, timestamps, and pointers to the file's data block. Okay. So all the file system on a Linux system are mounted under a single directory tree with the directory / at its root. The location at which a file system is mounted in the directory tree is called its mount point. So a privileged process can mount and unmount a file system using the mount function and unmount system calls. Okay, so these are the two functions, mount and unmount. Let me just write down here for you. Mount, and for unmount you have unmount function or system call. Okay, so information about a mounted file system can be retrieved using stat VFS. Okay, so we are just going to do one example out of these three functions. So this is the stat VFS function that we are going to use. Okay, so let's go ahead and let's do an example related to the stat VFS. Okay, so this is the function that would basically return 0 if it is true, and it would return -1 if it is false. Okay, now let's go ahead and let's try to do the code. So what we would do, we'll just remove everything which is inside the main function, and then what we would do, would modify the library. Okay, so we just need the first one and the last one. Okay, and we'd modify the last one. All right, so we just remove these two libraries, and in here what we are going to do is that we are going to basically modify this sys/, and then we want to write here stat VFS. Okay, so you might be wondering that what this stat VFS function is and what it does. So the idea is that there are basically two functions. One of them, I'm not discussing it here, but let me explain to you. So one function is stat VFS, which is this one that we are going to discuss. The other one is fstat VFS. Okay, so the only difference between these two functions is in how the file system is identified. Okay, so for stat VFS that we are gonna do, we use path name to specify the name of any file in the file system. Okay, for the other function, which is fstat VFS, we specify an open file descriptor, which is also known as FD, referring to any file in the file system. Okay, so both functions return a stat VFS structure containing information about the file system in the buffer pointed to by stat VFS buff. So now let's go ahead and let's try to do some coding regarding this magnificent thing. Okay, so now what we're going to do, that first of all we're going to have a structure here. So we are going to have struct stat VFS, and then we're going to have a buffer. Okay, so, or we can buff here. Okay, then we are going to write here an if condition in order to identify if in case it returns an error, then what it should do, that it should print the error. Okay, so what we would do, would write here if, and then inside of that we'd basically call the stat VFS function, and inside of that we'd pass the argument, and that argument would be, first we're going to put a dot, and then we're going to put a comma, and then obviously we're going to pass this buf, which is buffer. Okay, and once we do that, we put a double equal sign, then we write here -1. all right, and after that, after the if condition, what I'm gonna do is that I'm gonna write here the error message, p error. Okay, if you remember that in the previous example we have also used it, so we'd say that error. Okay, simply. So then we put a semicolon here, and obviously we are not enclosing them inside the braces, the curly braces. So what it means that after if statement. Whenever you write an if condition, after if condition there is one statement allowed that would be considered by compiler as the part of the if block. Okay, so the rest of the things would not be considered as the part of the if block. So right after this we can have an else block. So we'd write here else, and for else we'd need curly braces, because now we are gonna have multiple statements. So if we don't have else, let's say, then that would be fine too, because first of all, every time the program would run, it has to go through the if block. So if we don't have any else statement, it means in that case we just have to put in system exit as well in the if statement. Okay, in the if block you can say. So now we'd write here printf. All right, and that is gonna be a print statement, and inside of that we're gonna write here each block is %ld, because this is a long integer. So for that we'd write here ld, and then we're gonna write here each block, it has a size of, we can say has a size of %ld bytes. Okay, and then what we can do is that we have to use this buffer that we have initialized. So we write here buf, and then we write here dot f, and then underscore fr size. Okay, so you can say that what this thing is. Okay, so for that, what I would tell you that this is a fundamental file system block size in bytes. Okay, so I'm repeating, this is what this f underscore fr size, this thing is a fundamental file system block size, okay, in bytes. So you can say, where does it come from? It comes from right here, okay, because we are using this header file. Now we would see that how many blocks are available out of the total blocks. Okay, so we'd write here printf, and we'd write here there are, then we write here %ld, okay, because this is a long integer. Then we write here blocks available out of %ld, excuse me. Okay, and in here we can put a /n so that it goes right on to the next line, and in here we can also put /n so that it goes to the next line. And then after that, what we are gonna do is that we're gonna put a comma here, and after putting a comma would write here buf dot f, and then we write here /bavail, excuse me. Okay, so once you write that, then again you put a comma here, and for the total size you write here buf dot f underscore bavail4. So it is the number of free blocks available to unprivileged process. Okay, and the other one, which is f underscore blocks, that is the total number of blocks in file system. Okay, see that we have an error here. So yeah, here, and then we can /n here, and hopefully now we are good. So we save this, C program, we hit enter, and you can see there is no error, so it has executed perfectly. So now if we just execute our binary file, you can see that it tells us each block has a size of 4096 bytes. Okay, there are 25954139 blocks available out of 30543520. Okay, so the next topic is directories and links. Alright, so an inode doesn't contain a file's name. Alright, so instead files are assigned names via entries in directories, which are tables listing file name and inode number correspondences. So these directory entries are called hard links. So a file may have multiple links, all of which enjoy equal status. Links are